Hello everyone. So in this video I'm going to be looking at three problems from chapter 20, 7, 26 and 72. So in problem 7 we have the diesel cycle, which is the cycle for the operation of an idealized diesel engine. It's shown in this figure over here, and the area is drawn there. They're describing the cycle, and they're asking us to show that for a quadratic reversible engine undergoing this cycle using an ideal gas, the ideal efficiency is given by this expression, this long expression here. So we start at A, go to B. So these are going from A to B and going from C to D are adiabatic. Going from B to C is isobaric, and going from D to A is isovolumetric. Right? So this is under constant pressure, this is under constant volume, and the other two happen without any heat exchange. So heat exchange takes place from B to C or D to A, and so we are required to find this efficiency of this engine. Right? So let's see if we can actually do it. So this is problem 7. Now they're asking for efficiency. So efficiency is just the work done divided by the heat input, but work done is of course QH minus QL by QH. So this comes to 1 minus QL by QH. Sorry, let me actually draw the cycle here so we will actually know what we're talking about. So this is the PV diagram. These are adiabatic, so P and V. Let's see, this is A, B, C, D. A, B, C, and D, and we're going this way over this. Okay, so there's going to be some heat input coming in here and some heat output to the lower temperature reservoir. Okay, and I'm not going to write down the expression for efficiency, but we're going to start with this and manipulate that. Now this one, this QL is taking place at a constant volume, right? So we can actually write this. So this is 1 minus CV times N times delta T. Okay, so delta T from B to A, let's say. Okay. Whereas the other one is taking place under constant pressure. So the expression we are going to write there is Cp and delta T B to C. Let's say. Actually, let me be a bit more explicit here, because these are both positive quantities just by definition, and this is a higher temperature curve. So for the QH, this is actually Tc minus Tb, and for the QL, this is going to be Td minus Ta. Okay. So these are both positive quantities. Everything is going to come out correctly. Now the ends, of course, cancel. The ends go away, and there's a simple relationship between Cp and Cv because it's an ideal gas. It's just this ratio is 1 over gamma. So this comes to 1 minus 1 over gamma Td minus Ta over Tc minus Tb. Okay. Now we want to express the expression they give us is all in volumes, so we want to use ideal gas law and then perhaps the adiabatic expansion, just going from these 2 points to manipulate this. So we are going to write everything, all these temperatures, in terms of the other quantities, right? So let's do that. So PV equals nRT, and so T is equal to PV by nR. So I can write this as 1 minus P. So the nR is going to be common to all of them, right? So I don't need to write nR all the time because it's just going to cancel at the end. I'm just going to write these PV terms. So this is going to be PD times VD minus PA times VA divided by gamma times PC VC minus PB VB. Okay. Now we notice that PB is the same as PC, right? So I can actually say that this is just PB, and I can take this into a common parentheses. And VA is same as VD, so I can just call this VA. and take those into common parentheses. Let's do that. So 1 minus, in VA parentheses, PD minus PA, divided by, in PB common parentheses, this is VC minus VB. Okay? Now, to make things more better looking and dimensions, I'll move this to the denominator of that one, and I'll move this to the denominator of that one. So these are the initial steps. I'm not going to complete this. So VC by VA, so PB goes to the denominator of those. So this is going to be PD divided by PB minus, I'm missing a gamma here, right? Yeah. PD by PB and PA by PB divided by gamma of VC by VA minus VB minus VA. Okay. Yeah. Okay. Perhaps you can't read it, but hopefully you heard what I said. So it's not minus. It's a division, and then you take these and manipulate these. So that's PD, PB. So well, this is perhaps better to put this at a PC rather than D. So make this PC and oh no, sorry. So instead of B, I'm going to use C. But for this, I'm going to keep that because they're going to be related to, so PA and PB, yeah, they're going to be related by an adiabatic cycle. So you just choose the points here by making the fact that VA is same as VD and PB is same as PC. Just try to connect points that are connected by adiabatic paths, and then you apply the adiabatic expansion formula to these, and you just actually arrive at the result. I'm not going to do this. This is algebraically straightforward but very tedious, so I'm not going to do it, and it's actually done in the solution manual, but this is how you basically proceed. You start with the definition of efficiency, and then you manipulate this a little bit to you make things look dimensionless by making appropriate arrangements, and then yeah, you just turn this into some connection over the adiabatic paths, right? And then you use the adiabatic expansion formula, and that thing comes out. Okay? Perhaps one thing that that's not trivial to see is that writing it in this form and the specific heats, and then writing the ratio of specific heats in terms of gamma, so you get something easy to manipulate. Yeah. But let's look at the other problem. Right. So the next problem is problem 26. So we have a restaurant refrigerator that is a coefficient of performance of 5. If the temperature in the kitchen outside the refrigerator is 32 degrees Celsius, what's the lowest temperature that could be obtained inside the refrigerator if it were ideal? Okay, so this is an application of a definition of coefficient of performance. Actually, you need to look this up, but once you look it up, it's a simple algebraic manipulation. Well, let me just demonstrate that. I mean, of course, if you know what you're doing, pretty much everything you do in this course is simple algebraic manipulation. So I'm not saying that to downplay the hardness or the importance of this. Right? So this is problem 26. So the coefficient of performance, I actually looked this up, is given for a refrigerator by TL by TH minus TL. Yeah? So they're asking, let me see what they're asking. I think they give the outside temperature, so they give TH 32 degrees Celsius. What's the lowest temperature? They're asking for T low. Right? So we are going to just solve this for TL. I move this to the other side. So coefficient of performance TH minus coefficient of performance TL is just TL. I move this to the other side and move this to the denominator. So TL is going to be coefficient of performance divided by 1 plus the coefficient of performance times TH. And this is going to be 5 divided by 1 plus 5. Now, one thing that can go wrong here is that to use this formula, you have to use temperatures in Kelvin. Okay? And that's given in 32 degrees Celsius. So this is 32 plus 273. Right? And this is going to give you something in kelvins, again, you'll need to subtract off 273 degrees Celsius from that. 273 degrees to make it into Celsius. And I think, yeah, I don't write down the answer, but it's something below zero. It's like minus 20 degrees or so. Okay? So first you need to know the definition, which you can look up, and then you need to be careful to add this and then subtract this 273 degree business conversion between the Kelvin and Celsius.